All right. So welcome everyone to the ECE for 421 or 1513. I'm Amir Ashouri. I'll be your lecturer for this semester. Hope we're gonna have an awesome semester together. Hope also you enjoyed your holidays. You came back fresh. As you might know, we had a record breaking of registrations for this semester, so we had to break the participant into four concurrent sections. So two of the subsections are going to be taught by Professor Histi. Section 3 is going to be taught by Professor Liang, and I'll be your lecturer for sadly or happily, I'll be your lecturer for Section 1. I'm a postdoctoral researcher at the ECE department. That's why I don't have that prof title. So you can just call me Amir anytime you had a question. All right, so let's get started. First of all, how many of you are grad students in this class? So not that many. All right. Okay, so I'm pretty sure you've already at least heard the machine learning and the bag of machine learning and AI at least once. Probably that's why you're in the class. I'm not sure if this course is a compulsory course for you or not. But yeah, so it encompasses, you know, a different variety of interesting problems we can use to tackle and optimize. So here there are a bunch of things that we can optimize and, you know, tackle using machine learning, the bag of machine learning using different techniques. So starting from the, you know, classifying images. After ImageNet competition came along late 2009, people started to realize they can, you know, optimize this process to classify these 1,000 classes of ImageNet in a better way. So ImageNet has more than 1 million training images and 50 to 100K test images. So every year there's going to be a competition. Whoever can classify them with lowest accuracy, with the lowest error rate and highest accuracy. So these are the results here, starting from 2010. So if you see, it was going pretty normal. Let me see if I can have this here. So as you see, 2010 and 2011, it was going pretty much in a linear scale, going towards optimization. And the breakthrough happened here, 2012, with a paper of Alex Krzyzewski and also Jeffrey Hinton. He was a student here at University of Toronto. So they could outperform the other, you know, competitors by a significant large margin. So the number you see here is the top 5. That was a top 5 error rate. So this means that if you have 5 guesses, so 1, 2, 3, 4, 5, given an image from ImageNet dataset, if you have 5 guesses, what's going to be your average error rate of classifying those images? So it was around 85%, plus minus 1, depending on the version of AlexNet. So later on, it was known as AlexNet paper, and it was sort of a breakthrough, you know, work in the convolutional neural network. And, you know, going forward towards today, so we are sort of in a 3 to 4%, 5% error rate. So the recent convolutional neural networks like ResNet or NASNet, or even some you know, variants of those, we are able to classify the images from ImageNet by, you know, by an accuracy more than 96%, which is incredible. And the last column you see here, that human column, if you Google online, that is the work of Andrei Karpathy. He was also I think he had his undergrad here, and then he went to Stanford for his PhD. So a couple of weekends he trained himself using a JavaScript he wrote with the images, and he tested, and that's the result of the test on himself. So it has been known as a human baseline for ImageNet now. So that's just one of the applications of machine learning you can use. that's for just classifying images. The other wide range of applications of machine learning is for natural language processing, just like what Google Translate does. And recently, we can use recurrent neural network for that. The other very interesting topic is applications in biomedical and medical applications. Just using MRI photos, we can use convolutional neural network or other type of machine learning models to diagnose the early stages of cancer, maybe. Or one of the other very interesting things that people are doing is for gene sequencing. So these consider each of these letters, one of the letters representing a DNA gene. So considering only have 4 or 5, you can have a combination of these 5 bit repetition with different variable lengths. So if you calculate the optimization space, it's going to be in the order of billions and billions. So you just have to do a summation of number of parameters, and this is the sequence size, and this is the number of parameters, I equal 1 to the n, which is the upper bound of your sequence. And so if you just have like 5 or 6, just calculate this, you're going to see that you're going to have 1,000, 10,000 of them. So just suppose you have 22, if I'm not wrong, gene, and then you're going to have subsequences of them, and then you can concat them and generate new genes. So it's going to be in order of billions and billions. So definitely this is an interesting and open topic for now. The other, mostly well-known application of deep reinforcement learning was happened 2016 and 17 with the AlphaGo team of Google's DeepMind. They could beat the guru of the AlphaGo game, I guess 4-1 if I'm not wrong. And the agent was self-taught, and he learned by himself by playing against himself, and that was sort of a breakthrough for a deep reinforcement learning as well. So you just have to take a look at your cell phone and all the applications it does and it uses. So you're going to see you're surrounded by applications of machine learning everywhere. All right. Also on the research domain and industrial side, we had an influx of participant and registrations for like a state-of-the-art conference, which we call NIPS. So it's one of the top-notch conferences of the field. This year they changed the name to NeurIPS for many reasons. But yeah, if you see if you see the scale of participant here, they started like 5 years ago. The participants were like around 1K. So like it was like 1K here, and then 1.5, and going toward 2K. But then here, just look what happened this year. It was around 10K. So you see on the research side, there is also a huge interest. So actually, this is a tweet of a colleague of mine. So last month, when we were in Montreal, just look at how huge the plenary room was. Actually, you couldn't see the speaker; it was in perspective. So you need to have maybe binocular or something. So, and even this room was getting full. So if you were late for like 5 minutes, we couldn't enter the room. So at some point, some of the sessions it was overflown. All right, so that's just a sort of a word cloud of machine learning jargons you're going to see, or you might have seen previously. So we're gonna touch on many of them in this course. So basically, this course is gonna teach you some fundamental background and theoretical knowledge, also some applications of recent advances of machine learning and deep learning. So first of all, we're gonna start with supervised learning. Yeah, sometimes my presentation is getting messed up, so I have to exit and come back. I don't know what's wrong with the Mac here. Yeah. So mostly we're gonna start with supervised learning method. So supervised learning is one of the well-known and the most used subcategory of machine learning models. So it's happening when you have labeled data and you know what the label of the data is. When you train your model, given the label, you can optimize your training process using any optimizations. So in neural network, they use backprop. In linear models, they use other type of loss functions. And so it has been used since, you might not even believe it, it was late 40s. So the first perceptron was introduced late 40s. So it's a pretty old, but it's still open issue in many subdomains. So the other interesting category of machine learning is called unsupervised learning. So when you have a bunch of data, you don't know the label. Like you have a bag of coins, for instance, and you want to just cluster them in like 4 or 5 category, but you don't know what the label of the coins are. You might be able to use other features like weights or the shape, but you definitely don't know when you divide these two, set of coins, you don't know what they are. So given that problem, which is a little bit harder than the supervised learning, what we can do. And in this semester, we're going to learn about clustering, we're going to learn about density estimation, and a well-known technique called principal component analysis, or PCA. Also recently, so PCA, so which is here, PCA mostly applies linearly on your data set. So recently, for the deep learning domain, we have autoencoders. That does a job in a nonlinear way. I don't think we're gonna have time for that, but I'll try my best to go into a little detail about it if we have time. All right. Also, since you are a computer engineering student, so you definitely need some learning theory and also learning principles. So these two will help you to gain some, fine-grained knowledge of the backend of the process. And because, given the current tools like TensorFlow, Caffe, or PyTorch, or other things, by just like 5 lines of code, you can start training a neural network model. And if you don't know what's happening in the backend, it's not going to be good, because in many of your applications and problems, you need to have a complete understanding of the whole stack of the problem. We try to have a balance between the theory and application in this semester. This is my first time teaching this course, but I've heard and I've read some of the comments from last semester. So we are trying our best to adapt to to introduce more recent techniques as well. So you're gonna be more happy. And at least on my side, if you needed any like more change, or if you had any comments, just feel free to email me. I'll try my best to just adapt. But I think given the structure of the course we set for this semester, is going to be much better, hopefully. All right, so from now on, I'm just going to skip through the techniques that I already mentioned, so you have an overview of the things you might learn this semester. So starting from an good old linear classification. So we're going to start it from next lecture, I guess. So suppose you have 2 different classes of data, so like +1 and -1. Let me see. So you have these 2, which are labeled. That's why we already know what they are. So we want to understand, can we classify them using a classifier, which is this line. How well can we fit this line in order to classify these 2 types of data, so that when we finish training, we have the highest accuracy? That means that all of the pluses are classified in a separate domain, and all the minuses are in a separate one. This has one precondition, which is your data should be linearly separable, because this is a linear classifier. So you're going to learn other techniques that if you face a nonlinear data, or it didn't have the property of being linear separable, what you can do to transform them to a linear property, then apply linear classifications, or directly apply nonlinear classifications as well. So you're going to learn about them this semester. Another technique that you learn after linear classification is regression. So regression gives you the the fine line. So in this case, since you had a 3D space, normally your classify is one dimension lower. So when you have 3D space, you have a hyperplane in this case. So it classifies your data point, and given how far and how close you were, this hyperplane was with your data points, you're going to calculate the error rate using a technique we call it least square. And so the lower the error rate, the better the quality of your model will be. So this is an example of having a nonlinear data. So on the upper left side, you see that this data is not linear. It doesn't have the property of being linear separable. So you have to apply a transformation before that in order to make it linear, and then apply your linear classifier. There are other techniques as well, so we're going to touch on that as well when we reach that point of the course. In general, we are trying to, in machine learning, we are trying to find a sweet spot between classifying data so that neither we overfit it nor we underfit it the data. So you can use the most sophisticated 17th order polynomial like on the right side, and so like this is your data, these points, and the red line is your classifier. So you can apply using linear algebra or derivatives or other techniques, and you can find a fine-tuned classifier like this that has the highest accuracy for this specific data. But if you change the data after you train your model, when the test data comes and you wanted to predict for a new set of data, since you overfit it for that specific data very, very much, so you're going to lose the accuracy for a new set of data. So this problem is called overfitting. On the other extreme end, we call it underfitting. So for this sophisticated data, you just use a linear classifier, which of course doesn't give you the best accuracy. So we are trying to understand how we're going to be able to find a sweet spot in the middle of being underfitting or overfitting the data. So your model will be more robust. All right. After your midterm, you're going to learn about support vector machines or SVMs. You're gonna use some quadratic programming and Lagrange duality framework in order to find the exact margin that you're going to use here in order to find your classifier and your support vectors. So this would be after your midterm. Also, we can use SVMs to apply nonlinear transformation, and you're going to learn about them as well. So one of the things that we focus a lot in this semester is going to be neural networks. I'm pretty sure that that's the most exciting one you want to hear about. That's why I pushed the course materials to have more recent topics on that as well. So after neural networks, you're going to learn about deep neural network, and for a week or so, you're going to have some lectures about convolutional neural network and RNN as well. So for one of your assignments, you're actually asked to implement a backprop algorithm from scratch, which will help you understand how we're going to optimize and update the weights in a neural network. So as you might know, they are pretty old, like might be even late 50s or early 60s, but before the advancement of GPU and parallel computing, they were not efficient to compute because of the workload they required. So it wasn't until 2010 or late 2000s that people realized now they have the power to compute the neural network, and that's why their network got bigger and bigger, and deep learning came to phase, and we have so many of other variety of deep learning models like CNNs, RNNs, GANs, autoencoders, deep reinforcement learning, and other things. But the concept is the same. So you have an input layer and you have an output layer. So you'll be able to, so every time the output of the first layer is going to be the input of the hidden layers or the next layer, the subsequent layer. That's why in order to calculate the HFI for the layer 2, the hidden layer 2, you're going to have a function, a nonlinear function, we call it theta here, which is a summation of all the weights of the neurons multiplied by the input, but the input was the output of the first layer. So the output of the first layer comes as the input of the second layer. And then, so this is a normal, so that's what we call vanilla neural network, in which all the layers are fully connected. You see all the neurons, we didn't show it here, but all the neurons here were fully connected to the previous neurons. And in convolutional neural network, that's what we use for image classification. You see that not only we have fully connected layers, but we have convolutional layers that convolves with the images. But for now, just you see it, all the fully connected layers, and at the end, the output layer, you normally sometimes they call it softmax in CNNs. In this case, we wanted to classify using a sign, so the output was either plus or minus, using the output of the previous, the hidden layer number 2, and we would just have an output layer with the output Y we were looking for. So there are so many things that we could talk about for neural networks. Actually, it would need a separate course for itself, and I'm not sure if we could finish it, in just one course. But we are trying our best to, introduce you all the learning and optimizations you need in order to train a good neural network, and also how you're gonna expand your knowledge towards CNNs and RNNs. So when you have an optimization problem that you want to tackle with neural networks, so you need to have a formulation of your loss function, and you want to minimize that loss function. And suppose if you draw that in a 3D space, so that's going to be the optimization space you are traversing, starting from any of these points, suppose that point, and you want to reach towards the minimum loss point, which is this, and you want to, when you hit one of the local minimas, like that, you want to surpass it, and you don't want to stop there, you want to go towards your global minima. So there are so many other techniques that help you in a neural network domain to do that, and we sort of listed some of them, like stochastic gradient descent, backprop, how we're going to regularize our weights using dropouts and other techniques, and at the end you're going to see something about convolutional neural networks as well. So the whole bag of optimization will help you to traverse your training step, starting from step number 1 towards the right direction at a step maybe number 10 million, towards the minimizing loss function using that formula. All right. So, any questions so far? So after the vanilla NNNs or deep neural networks, you're going to learn about convolutional neural networks. So a convolutional neural network is a variant of DNNs, with the exception that it accepts an image as inputs rather than some other weights. And these layers are, instead of being a fully connected layer, they are convolutions. So they contains a number of filters with a specific width and height, and so these can convolve through your input image and extract either low-level features, and going on towards further deep into the network, you can have higher-level features, and then at the very end, normally have some fully connected layers to do the final classification using a softmax layer. So you're gonna learn about all of those after we pass through the neural networks, and this will be maybe in a month or so. All right. After your midterm, you're gonna start seeing some unsupervised learning, So as I mentioned before, so suppose you have a number of data points that you don't have any labels for them. So that's why it's all blue. So there are a number of techniques you can use in order to cluster or, gain some information out of those data. And you're going to see some like k-mean clustering, how we're going to cluster them into n clusters. Or also you can, you're going to learn about density estimation, how we're going to estimate the density of the samples. After learning this, if you were interested, I would strongly advise you just to learn about generative models recently, or GANs. I try my best to present you at least at some level the GANs and some of the application and how we're going to do the optimizations. But since it's a huge bag of topic for itself, I'm not sure how well we can go into details. Another well-known technique that was there for a long time, and you might have heard it a lot, is called principal component analysis, or PCA. So PCA basically transform in a linear way your data point from this and rotate your axes in a way that the space is getting shrunk. So that's why it's one of the optimization techniques in reduction of dimensionality, actually. So dimension reduction technique, is what we call it. As I mentioned, it does so by a linear, method. But recently we have autoencoders that does so by a nonlinear job. So we also have some details about it when we touch on PCAs. All right, that was mostly your supervised and unsupervised learning methods. So in order to use those, you need some theory. How you're gonna start from training data with your ground truths towards your output of learning. How you're gonna calculate your in sample and out of sample error when you have multiple data sets. And using that, how you're going to use a learning algorithm called pack learning and VC dimension. How you're going to describe your complexity of your data set using a VC dimension, which is this line here. So this line represents your complexity of data. This is the highest number you can find, and that's called your VC dimension. So we're going to touch on that as well when we reach. And for techniques, you're going to see how you're going to make your models more robust using cross-validation, how you're going to differentiate your training and validation sets, and later on, how you're going to optimize your training process. Again, not to fall into any of these overfitting or underfitting pitfalls. How you're going to regularize your weights. Suppose when you are training a neural network, what hyperparameters normally are suitable. And so one of the two famous techniques that has been proposed recently are weight decay method and dropout that we're going to talk about. So about the logistics of the course, as I mentioned, I'll be your lecturer for section 1. We have 3 more sections. Since this course has 16, I think we have 16 TAs. So we have a head TA. So she's going to be your main point of contact for all the course logistics. So feel free to contact her if you need any help. Also, we have lab office hours on Tuesdays, 4 to 6 p.m. You can find this slide also online on Quarkus. For the course textbook, the main source was learning from data. But since this book was introduced, I think before 2012, there were a bunch of other techniques that were well known after that. So if you go to the website, there are some supplementary chapters for more recent techniques like neural networks and deep learning, or if you wanted to have more variety of options to have more videos and materials, you can have a look at the video lectures, and there is a discussion forum for that. Also, there is a very nice book by a young good fellow and his collaborator that is freely available online. It's called Deep Learning. So you might know him. His work was very famous in the GANs recently, and other things as well. Also, as you know, we have another course for the CS department. So that textbook is also recommended if you wanted to have, another source of. I mean, definitely if you search online, there are tons of materials, but here are a bunch of them you can use for that. So that's going to be your tentative schedule. We mostly try to start with supervised learning, and then in February we're going to go towards neural network, and we're going to have a week or so about deep neural networks, where I'll explain about CNN and RNNs. So there, one of these assignments, I think this might be, is the one you have to implement from scratch your backprop. So I strongly advise you just to do it yourself. You might fail once or twice, but it's going to be easy at the end. It's just some derivatives. Yeah.
Is there a reason why we cover SDMs at the end?
No. Yeah. Because unsupervised learning wasn't, having that much of content, so you had to split it in a way. Yeah. But yeah, if you wanted to split it in supervised and unsupervised, it would be in the first section. Yeah. So so after the midterm, you're gonna have more unsupervised, pack some theory, and at the end, the SVMs. You're gonna have also on weekly basis tutorials. Being presented by your TAs. So this is the list of tutorials and the place and the days you can find. So they're going to be starting from this week as well. So for the prerequisite of the course, I'm pretty sure you're all familiar with some backgrounds in probability. And also some linear algebra, how we're going to define and use vector space notions, and multiplying matrices, so on and so forth. It's not a big deal. But I'm pretty sure you're fine with that. I mean, the fact that you are in this university shows that you don't have any problem with that, hopefully. And for the programming language, we chose Python and TensorFlow. So as you know, TensorFlow was introduced by Google in 2015. Its backend uses mostly C++, but on the front end you can use Python or any other language to communicate with the API, and it can generate codes for many different backends, like for GPUs, FPGAs, CPUs, or even mobile devices. So GPU support is not required, and that's exactly what we're going to use for, and what you're going to use for your assignment as well. Also, for the instruction, there are tutorials online. Just check Kirkus website, so you're going to see some PDF, and also online in tensorflow.org there are tons of materials available. So for the grade, undergrads will have 30% from their midterms, which will happen on March 1st, and then the assignment will bring you 30%, and the final exam will be 40%. For grad students, you're gonna have another extra assignment that and brings down your midterm 15%. So that will in total cost you 30% as well. So you're gonna have more fun. All right. So that's just an example. So any of you can't or haven't programmed with Python at all so far?
Haven't.
I haven't. Yeah. Any other languages? It's gonna be easy for you because Python is like speaking English. That's fine. Yeah, I think you. So I mean, so that's an example for TensorFlow. As you see, it's pretty easy to start training a neural network with a ready data set like MNES here. But if you don't know what's happening underneath, under the hood, there's no difference between you or a high school student that just start learning this. And believe me, if you work outside university or if you decided to have a grad degree, learning what's happening when you just call that tf.nn.softmax, if you know exactly what's happening underneath, it's going to help you optimize your your application using a variety of things that the others can't. So and this is going to be your leverage point in respect to the others. So as an example here, using this 5 line of code, when you install TensorFlow, you can import the library as TF, and then you're going to define a placeholder for which has a data type of float32, and so the size would be 784, and the batches could be in any size. That's why you put it none. And then you are defining 2 more variables for your weights and biases, and then the y would be from this class you instantiate tfnn softmax, which does the matrix multiplication with x and w, and you add the biases at the end. So you see, with just 5 lines of code, you could start initializing a computational graph. And the blue box represent the way you define your loss function, and you're going to learn about them here. So as I mentioned here, there are a variety of optimizations you can use in order to traverse the optimization space and minimize your loss. So each of them has been defined. So instead of writing the code, all of them are available with just 1 line of code here. So here you define that this is your cross entropy, and you want to use the gradient descent optimizer with this hyperparameter to optimize it at each training step. And then when you want to run it, either using an interactive session or session.run, you start traversing through your images, and the images come from MNES dataset. And then at every run, you're going to feed the input image, and you're going to optimize it here. So you see, it's pretty easy to train a deep neural network nowadays with TensorFlow. But what's important is the knowledge you have under the hood, what's happening in the background. And that's pretty much everything I have here for today. So starting from Wednesday, we're going to start with linear classification. Any questions? Yeah.
Did you mention for the assignments, is it individual or do we do it with a group or something?
I guess for the back prop it is individual, but I can get back on you with that. I'm pretty sure 90% is individual.
Okay.
Yeah. How much of theory we cover when we? I did in the last word. Proofs. How much of theory we have to learn? It's not that much. And most of the theories are just linear algebra or just some probability theory. It's pretty easy for you. It's not like rocket science.
Will there be a lot of probability material covered? Like you said that the probability course is a hard requirement. They haven't tried taking it.
Yes, we have put some materials online at the Kirkus, but if you have passed, I think you had one course previously, right?
No.
You didn't have.
Well, long story, but
I'm pretty sure you're gonna catch up. It's pretty easy. It's not. Yeah. The CS course and this one? Oh, I don't know about that. What's the name of that? What's the title of that course? Maybe that one is mostly neural networks. Yeah, I'm not sure. I should double check that. All right. So have a good day, guys. See you on Wednesday.